All right, so this is really interesting stuff. It can seem complicated, so I'm going to try to make it as simple as possible. I'm going to try to be very thorough and provide numerous examples. So this is going to be a long video. If you're familiar with parts of it, feel free to fast forward. But if not, take your time, make sure you get it, because we're going to use the same concepts over and over again to solve what look like somewhat complex problems. Okay, so the goal here is to find rational, irrational, and complex zeros of a polynomial. In other words, to find all the zeros of a polynomial. And this is tough. Mathematically, this is a hard thing to do. And the techniques we're going to look at here don't always work. Finding zeros of polynomials is difficult, okay? And in this video, we're going to look at cases where we can and some techniques that work. So let's start by discussing the types of numbers we're talking about, rational numbers and irrational. So rational numbers are numbers that can be written as a ratio of two whole numbers. Okay, so like 2/3 is a rational number. 0.6 repeating is a rational number because it's 2/3. Okay, so rational numbers here, as far as polynomials go, where the coefficients are rational, what we're talking about here are numbers with no square roots or I. Now that's not a complete definition. The number pi is not a rational number, okay? But it does not have a square root or an I. But as far as we're concerned with these types of polynomials, when we say rational, that means there's no square roots or I, okay? So no problem. Now, irrational numbers, by definition, are numbers that cannot be written as a ratio of whole numbers. So pi is not rational. It's a decimal that goes on forever and doesn't repeat. E is not rational. It's a decimal that goes on forever and doesn't repeat. But for the purpose of polynomials, irrational numbers have a square root. And what I mean by that is a square root that doesn't simplify and go away. So if you have the square root of 25, don't call it that. Just call that 5 with no square root. That is not an irrational number. It's rational. Now these two types of numbers all together, the rationals and the irrationals, make up the real numbers. Okay? The real numbers. These are real numbers are numbers that live on the number line somewhere. Okay? Just to make this very simple. Now, the unreal numbers are called complex numbers. Complex numbers involve the imaginary number I, okay? Have the imaginary number I. If you need to go do research on any of these things I'm talking about, go do that before we go through this. I'm not trying to teach you about the number systems in entirety, just how they relate back to the polynomials we're going to look at. So complex numbers are not real numbers, okay? These are not on the number line. We can't plot the number I on our real number line, okay? So that's a quick rundown of the types of numbers we're talking about and how to recognize them. Let's get on to how do we determine the zeros of a polynomial, real or unreal, right? Okay, so the main concept here. Let's talk about the main concept that we'll try to emphasize throughout every example. The main concept. The first thing you want to do if you want to find zeros is try the most basic techniques. Now, factoring is a useful concept when you want to find zeros because there's always this relationship between factors and zeros that I've explored in a different video. And we'll see an example here, so don't worry about that. So the first thing you want to try is try to factor. Okay, so try to factor using your basic techniques like a greatest common factor, difference of squares, the AC method or trial and error, factor by grouping, whatever it is. Use your basic techniques first if you can. Now most of the examples we're going to look at in this video these basic techniques don't work because I want to get to the more advanced techniques, okay? All right, so if your basic techniques don't work, then you can't go further unless you can find rational zeros So the idea now is we're going to divide using synthetic division. Divide using synthetic division and enough rational zeros. We talked about rational zeros and how to list those in another video. But divide using synthetic division and enough rational zeros to get down to a quadratic polynomial. To get down to a quadratic, a degree 2 polynomial, okay? So, if you're starting with an x cubed polynomial, you would need to divide one time to make that an x squared polynomial. So you would need one rational zero. If you have a degree 4, a quartic polynomial, to get that down to degree 2, you would have to divide once and twice. You'd have to have two rational zeros to get down to a quadratic. So that's what I mean by this. Divide enough times to get to a quadratic. Now sometimes you may have a quadratic and you can skip this because you wouldn't have to do any dividing. Once you get to a quadratic, you can find the zeros of the quadratic. Find the zeros of the quadratic using a square root or the quadratic formula, depending on whether you have an x term or you don't have an x term. So, basic techniques, if they don't work, find some rational zeros, divide enough, and then find the zeros of the quadratic. So that's the main concept that we'll emphasize throughout the entire video in every example. Now, finding zeros has many uses, so I'll try to give you some different sets of instructions as we go along so you can see how to use them. But the first one we're going to look at is simply going to be find the zeros, meaning all of the zeros, okay? And the polynomial we're going to start with is a quartic. X to the fourth plus 7x squared minus 18. Okay, so the first thing we're going to try are our basic factoring techniques. And they might work in this case because it's a basic trinomial, and the first term, its exponent is twice as much as the exponent in the middle. So in fact, if we try to factor this, it's pretty easy. Because of the pattern of the exponents here, and the numbers happen to work, I'm going to set up two binomials, and to get x to the fourth as my first term, I'll use x squared and x squared, which when I combine all of this would give me an x squared in the middle, so that's good. Then I'm looking for two numbers that multiply to give me negative 18, but that add to 7, so that would be positive 9 and negative 2. Okay? Now, I need to find the zeros, right? So if I want the zeros, I need to know when this whole thing equals 0. So now, if I want the zeros of this, I would have to set that equal to 0 and solve it. And to find the zeros of this, I would set this equal to 0 and solve that. You see how these are quadratic, so I don't have to do any dividing with my rational zeros. These are quadratic, so I can go ahead and find the zeros. Fantastic. So now, if I want the zeros of this, I'll subtract the 9. And I'll take the square root of both sides, so I'll have plus or minus the square root of negative 9. And the square root of negative 9 is 3i. Okay? 3 times the imaginary number I. So we get some complex zeros. We get 2 of them out of this factor. Over here, add 2 to both sides, take the square root, and we get plus or minus the square root of 2. So the zeros, the answer to this question, the zeros of this quartic polynomial are 3i and negative 3i, positive square root of 2, and negative square root of 2. So these are the 4 zeros of this quartic polynomial, 2 of which are complex, 2 of which are irrational. So you can see that this particular polynomial does not have any rational zeros. So if you made a list of potential rational zeros, there would be numbers on that list, but none of them would actually be zeros of this polynomial. So the only way you could find the zeros is to do something like this. All right, let's do another. Just a heads up, for every upcoming example, the basic factoring techniques won't work, okay? So that's the only one we're going to do like that. So in example 2, I'm going to give you a different set of instructions. So I'll ask you to solve, and we'll solve this equation, 2x cubed minus 5x squared minus 20x plus 11 equals 0. So what we're asked to do here is to find the x values for which this polynomial equals 0. That's precisely asking you to find the zeros of the polynomial. Figure out what makes it equal 0. So what we do is we look at we go through our process and we think, okay, we need to try our basic techniques first. So since this has 4 terms, you might think to factor by grouping. So what we're going to do is we'll try that. So out of my first 2 terms, I can pull an x squared, leaving 2x minus 5. And out of my second group, they have nothing in common, but my first term's negative. So I'm going to pull out not a positive 1, but a negative 1, because 1 always goes into everything, leaving positive 20x minus 11. And you can see if you try that, the grouping does not work because the 2 binomials here don't match, which is a requirement when you do grouping. So that doesn't work. So now we're stuck. We've got to make a list of potential rational zeros, right? So possible rational zeros. And if we look at this polynomial, it's cubic. I need enough rational zeros to make this cubic into a quadratic. I need to divide 1 time to make a degree 3 into a degree 2. So when I look at my possible rational zeros, I just need one of these guys to work. I need 1, okay? There might be more than 1 from this list that works, but I don't care. I'm just going to stop when I find 1. So I need to look at my numerator. My numerator can be any factor of 11. So that's 1 or 11. My denominator can be any factor of 2. So that's 1 and 2. And of course, I could have plus or minus any of those. So when I go to make my list, I could have 1 over 1. So I could have positive 1 or negative 1. I could have 11 over 1, which is 11, or negative 11. I could have 1 over 2, so that's positive 1/2, negative 1/2. I could have 11 over 2, so positive 11/2, negative 11/2. Those are my possible rational zeros. I'm going to run through the list, not necessarily in any particular order, and see if any of them are zeros. Now, 1, I always like to test in my head. So 1, I just plug in and see if I get 0, right? Because I can ignore the x's when I plug in 1. So 2 minus 5 is negative 3, minus 20 is negative 23, plus 11, that's not 0. So I can go over here and I can cross 1 out because I know it's not a 0. It never will be. Now let's test negative 1. We could do it the same way, but let's go ahead and start testing with synthetic division. So if I test negative 1, I have 2, negative 5, negative 20, positive 11. And what I'm looking for is a remainder of 0. So I'm going to run through my synthetic division. I'll drop my 2, and then I start multiplying and adding. So I get negative 2, negative 7, positive 7, negative 13, positive 13, I don't get a remainder of 0. So that guy did not work. I can cross it off my list. That's not going to be a rational 0 that works for us. On your paper, I probably wouldn't erase. I'd probably keep writing just so you have a record of what you've tried, but I don't have a lot of real estate here to work with. Let's try 11. Drop my 2, multiply, get 17. 11 times 17, oh boy, let me get my calculator here. Well, 10 times 17 is 170, so I need one more 17, which is 187. Okay, never mind. Add those together, you get 167. And then you can see 11 times 167 is not going to give you a remainder of 0. Okay? So 11 doesn't work either. And based on the same idea, I'm probably going to skip negative 11 and assume it doesn't work because it looks like the numbers will probably get too big. I can always come back and test it if I need to. Let's go to 1/2. So drop my 2. And you might be scared of the fraction, but in this case, it actually works out nicely because immediately when you multiply 1/2 by 2, you get 1. Add and you get -4. Multiply, you get -2. Add and you get -22. Ooh, this looks good. 1/2 times -22 is -11, and we get 0. Okay? So 1/2 is a rational 0. We've got 1 0 so far. It's degree 3. We should expect 2 more. And somehow this gives us a quadratic. And you can see, when you divide a cubic one time, you get a quadratic. So this is the quadratic that we're looking at, and we need to find the zeros of this guy, okay? We need to find the zeros of this. This is quadratic. So what I would do at this point is I'd factor the 2 out to make it easier. Actually, what I'd do is I would divide both sides by 2. Because dividing both sides by 2 is just going to make the numbers on the left, the coefficients over here, smaller, but it's going to leave the right side as 0. Now, if you missed that, it's okay. You can use the A, B, and C that are given here, but you'll have bigger numbers. So this is the polynomial. We're going to go to the quadratic formula. So negative b is positive 2 plus or minus the square root of negative 2 squared is positive 4 minus 4 times 1 times negative 11 all over 2 times 1. Okay? So we get 2 plus or minus. Okay, so we've got 4 minus negative 44. So that's 4 plus 44 is 48. So I've got the square root of 48 over 2. And then you can use your calculator or whatever, but 48 splits apart to be 16 times 3. And the square root of 16 is 4. So this is the same thing as 4 times the square root of 3. And then since both of these terms are divisible by 2, I could rewrite this as 1 plus or minus, right, I divide both by 2, and I get 1 plus or minus 2 square roots of 3. Okay? So I've got 1/2 as a 0, and I've got these guys as zeros. So let's come over here and write our final answer. If I want to solve this equation, I get 3 solutions. So x could be 1/2, 1/2. That's okay. X could be 1/2. It could be 1 plus 2 times the square root of 3, or it could be 1 minus 2 times the square root of 3. There are 3 possible solutions to this equation, and in fact, those 3 x values are the 3 zeros of the original polynomial. Okay? So very good example here. We had to find a rational 0, just 1. We divided, we got a quadratic, and we finished using the quadratic formula. It's the basic principle of this entire video. Let's move on to another degree 4. Let's move on to another degree 4, and let's say we want to factor it. Factor into linear factors. Okay? Factor into linear factors. And the polynomial we're looking at is x to the 4th minus x to the 3rd plus x squared plus 9x minus 10. Our basic techniques do not work here because this has more than 4 terms, so we can't even do grouping. So we immediately default to possible rational zeros. We look at rational zeros, and if I want to take a degree 4 and make it a degree 2, I need 2 rational zeros. I need to divide twice. So I need 2 of these guys. Now my possible numerators are the factors of 10. So that's 1, 2, 5, and 10. And then my possible denominators are the factors of 1, which are just 1. So that's nice. And I could have positive or negative. So I could have 1 over 1. I could have 2 over 1. I could have 5 over 1. I could have 10 over 1. So that's my list that I'm working off of. I need 2 of these. And by the way, you could have two different zeros, or sometimes 1 0 could work more than once. So you've got to keep that in mind. So let's test 1 first. And again, I like to test 1 by plugging it in. So I get 1 minus 1 is 0, plus 1 is 1, plus 9 is 10, minus 10, 0. 1 works, okay? So 1 works. I need to do my division. So I have 1 x to the 4th, negative 1 x cubed, positive 1 x squared, positive 9x, negative 10, and I should get a remainder of 0. So I drop this 1 and I multiply and I add. Multiply, add, multiply, add, multiply, and add. And so that's what we get. Now this guy here, this polynomial is an x to the 4th. When I divide, it turns into an x cubed. That's not quadratic, so I need to try this process again. So I need to continue searching through this list for 1 more 0. And the big thing you need to understand here is you do not divide by the original now. You divide by this new guy, 1, 0, 1, 10. This is our polynomial. This is our remainder, right? So that's sectioned off. This is our polynomial. This is our cubic that we need to divide 1 more time to get a quadratic. So I'm going to continue working off of this list. 1 worked. You want to try it again because it could work again. You'd hate to not try it again and go through all those others and none of them work. So make sure to try 1 again. So again, drop your 1, multiply and add, multiply and add, multiply and add. That didn't work. So 1 did not work again. Okay? Again, on your own paper, you'd probably leave this as showing your work. I'm going to expedite the process here. We test, we test, we test, and we eventually get down to negative 2. Right? Again, there's no particular order that you're testing these in. So you need to be proficient with your synthetic division. It's basic arithmetic, shouldn't be too bad. So drop your 1, multiply, add, multiply, add, multiply, and add. And we can see that negative 2 is a 0 and that 1 was a 0. The result here is, remember this was x cubed. When we divide, we get x squared. So this is our quadratic. X squared minus 2x plus 5 is the quadratic. We'll use the quadratic formula to find the zeros of it. So I'll label maybe quadratic formula. So we have negative b, which is positive 2, plus or minus the square root of b squared, that's 4, minus 4 times 1 times 5, so that's minus 20. All over 2 times 1 is 2. So we get 2 plus or minus the square root of negative 16 over 2. The square root of negative 16 is 4i. Switch purple markers here. So this just turns into, again, because both of these are divisible by 2, I can just divide and get 1 plus or minus 2i. If this didn't reduce, then this would this would be your 2 zeros, okay? But it does reduce, so we get these guys. All right, so what we were asked to do is factor into linear factors, okay? So we've got our 4 zeros now, 1, -2 in both of those. So let's list those out. So our zeros were 1, -2, 1 plus 2i, and 1 minus 2i. Those are our zeros, but this problem asks us to factor this polynomial. When you factor an x to the 4th, you're going to get an x something times an x something times an x something times an x something. You're going to get 4 sets of parentheses with an x, something like this. You're going to have x, 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 and x, okay? Now, how do I know what goes in here? Well, if you know your zeros, you can easily create factors by doing x minus each of these, all right? So this turns into x minus 1. This turns into x minus -2. This turns into x minus 1 plus 2i. And this turns into x minus 1 minus 2i. Now, the other thing you want to look for is make sure that your leading coefficient matches. If you were to multiply all of this together, your first term would be x to the 4th, 1x to the 4th. But sometimes this could be a 2 or a 3, and you'd have to adjust your coefficient by copying it here. So just for emphasis, I'm going to put a 1 there to make sure that this coefficient matches that coefficient, okay? Now, if we clean all of this up now, it just turns into x minus 1 times x plus 2 times, distribute the negative, x minus 1 minus 2i times x minus 1 plus 2i. So each of these are linear. They're all x to the 1st factors. And that's what we're supposed to do. So let me emphasize what's happening here. If you factor this polynomial right here, you get this. And some of the zeros are rational. The 1 and the -2 are rational zeros. And then the last 2 zeros are complex. So in order to factor this all the way down to linear factors, you have to use complex numbers. Very interesting to see this. Okay, let's do 2 more examples, it looks like. I told you there'd be a lot of examples. I want to be thorough here. Want you to see different applications of the same concept, right? All right. So let's look at the next one. The directions here are find the zeros. But I'm going to tack on, I want to know their multiplicities also. Find the zeros and their multiplicities. And the polynomial is 9x to the 4th minus 33x to the 3rd plus 28x squared minus 9x plus 1, okay? And so our basic techniques don't work. There's simply too many terms. So we make a list of potential rational zeros. And since this is degree 4, I need 2 of these to reduce this down to a quadratic. So my numerator are the factors of 1, so that's just 1. My denominator could be any of the factors of 9, which are 1, 3, and 9. So when I make my list, I could have 1 over 1. I could have 1 over 3. And I could have 1 over 9, okay? Now, I've already done some of the work, so I'm going to save us some time here. I'm going to start testing these, and 1 does not work. 1 does not work. -1 does not work. 1/3 does work, okay? So let's do the synthetic division here. let's see, 9, negative 33, 28, negative 9, 1, okay? So 9, 1/3 of 9 is 3, negative 33, yep, negative 10. Okay, so just making sure I'm on track. Add and we get 18, 6, negative 3, negative 1, 0. So we get a remainder of 0. Now this was x to the 4th, so now we have an x cubed. We need to divide again. So sometimes what people will do is actually, rather than recopying this, they would just continue, I'll use a different color now, they would just continue their synthetic division right here. Just make sure not to incorporate your remainder into this. It'll throw everything off. All right, now 1/3 worked, right? So that's one of our zeros. We need to test it again because it could work twice. So let's go ahead and test it. Drop your 9, multiply and get 3, add and get negative 27, multiply and get negative 9, add and get positive 9, multiply and get positive 3, add and get 0. So 1/3 worked again. And remember, this was x cubed, which means that this is x squared, and this is our quadratic. So what we see here is 1/3 is a rational zero twice. It has a multiplicity of 2, okay? Now we've got our quadratic, we need to find the zeros of it. So what I'm going to do is, that's negative 27x, I'll set that equal to 0, and I'll divide both sides by 9. That's going to make all my numbers smaller. Sometimes you can't do that, but it's nice when you can. And then we'll use the quadratic formula to find the last two zeros. So we've got negative b, positive 3, plus or minus the square root of negative 3 squared is 9, minus 4 times 1 times 1, that's 4, so 9 minus 4, over 2 times 1 is 2, okay? So we get 3 plus or minus the square root of 5, which does not simplify, over 2, and we can't reduce this, okay? So there are the last two zeros. So let's answer the question. What are the zeros and multiplicities of this polynomial? So 1/3 is a 0, but it has multiplicity 2. 3 plus the square root of 5 over 2 is a 0, and it has multiplicity 1. And last, we have 3 minus, yeah, you can still see that, 3 minus the square root of 5 over 2, and it also has multiplicity 1, okay? So you can see that when you look at all the multiplicities together, it adds up to 4. 1/3 showed up twice, and each of these showed up once, and that's always the case because this is a degree 4 polynomial. The multiplicities should add up to 4, okay? All right, so that I wanted you to see an example where a 0 could show up more than once. Okay, finally, let's do our last example. We'll go back to a cubic. And this one can be perplexing sometimes, but I'll try to explain it so that it makes sense. Let's say, let's find the zeros and their multiplicities. Find the zeros and their multiplicities again. And this time, we're looking at x cubed, we're looking at a cubic, plus 7x squared plus 16x plus 12, okay? I'll tell you right now, this has 4 terms, so you could try grouping, but it won't work. So we need to resort to our rational zeros. But this is cubic, so I only need to divide 1 time to get to a quadratic, so I only need 1 of these guys to work. My possible numerators are the factors of 12, so that's 1, 2, 3, 4, 6, and 12. My possible denominators are the factors of 1, so that's just 1. So basically I get 1 and negative 1, 2 and negative 2, 3 and negative 3, 4 and negative 4, 6 and negative 6, 12 and negative 12, okay? A lot of possible zeros. I just need one of them. And again, I've done the legwork for us ahead of time. 1 and -1 don't work. You can test these out. 2 and -2 don't work. 3 doesn't work, but -3 does. So let's do our synthetic division. So I've got 1, 7, 16, 12. So we're showing that -3 works now. This is what you would do to see that -3 works. Drop your 1, add, multiply, add, multiply, and add. We get a remainder of 0, but now since this was cubic, this is quadratic. So there's our quadratic. We need to use the quadratic formula to get the zeros of this guy. So we get -b, so -4, plus or minus the square root of b squared is 16, minus 4 times 1 times 4. So that's 4 times 1 times 4 is 16, over 2 times 1 is 2. So now we get -4 plus or minus 0. So we just get, so let's write that out, -4 plus or minus 0 over 2. So that's literally, you don't need to write the plus or minus 0. If you add or subtract 0, you get nothing. So you just end up with -4 over 2, which is -2. Now, what could that mean? We only got, right, -3 was a 0 one time, so it has a multiplicity of 1. And we got -2 as a 0. There's only 2 zeros, and we need 3. Well, the quadratic formula always yields 2 zeros in a way because of this plus or minus. Since -2 was the only one number that came out of this quadratic formula, it has to have a multiplicity of 2. So that's why I wanted to show you this example. So the answer will be that our zeros are -3 with multiplicity 1, and -2 has to have a multiplicity of 2 because the quadratic formula always yields 2. Now it could yield 1 0, and that means that it has a multiplicity of 2. It has to be a 0 twice. Okay? So those are the zeros and their multiplicities for this cubic polynomial. All right, so make sure to practice this, be organized, follow the big picture, don't get lost in all the details. Be very careful with your synthetic divisions because if you get a sign wrong, you could miss the rational 0 that should work. So just take your time, make sure you get all those right, and you'll probably start to enjoy this after you get the hang of it.